Great. All right, cool. Thanks everyone for joining today. We're going to be talking about is best practices we've learned for debugging connected applications running Zephyr. My name is Chris Coleman. I'm the co-founder and CTO at Memfault, where we build developer tools for embedded engineers to help them ship products faster and fix the issues they're seeing. Prior to starting Memfault, I worked as a firmware engineer myself at companies like Sun Microsystems, Pebble, and Fitbit, and a lot of connectivity and low power debug on embedded devices as well. I sit on the Zephyr technical steering committee, and I've made a few contributions myself. So, Luca?
Yeah, my name is Luka Mustafa from IRNAS in Slovenia, where we're creating IoT solutions. So really doing the applied engineering and taking things to the field with various clients. So my background is in the electrical engineering, but for the past 7 years, I've been running the engineering teams to create various products. And well, IoT is a very dear topic to me, so I'm excited to share with you guys some cool things we've been doing.
Thanks. Connected applications. In 2018, there was estimated 22 billion active connected devices in the field. And by 2030, it's estimated there'll be more than 50 billion. I expect more and more of those to be running Zephyr. On the right here, I have a picture of a LTE-enabled board, the NRF9160 that runs Zephyr. Connectivity stacks themselves are a lot more complex than some of the hardware of old. There's network stacks, there's protocol layers, there's interoperability issues that can arise. And so building together the right tool set to look at them can save you a lot of time, get the products to market faster, and make your users end users happier. And there's so many different applications for connected products as well. Luca, I want to mention some of the ones you've worked on.
Indeed. So to set the scene for today, I'll give a few examples of exciting things we've been working on. For example, the electrical grid is a very important topic for all of us, and particularly the digital world, as everything runs on electricity. But the infrastructure itself is still very much analog, and well, not many sensors are deployed on the wires, towers, and a lot of the physical objects in the real world, which tend to get damaged and so forth. So I'm showing an example of a few products which are either on high voltage lines, on towers, on various components, monitoring their performance over multiple decades on one end, and on the other end, looking at some infrastructure, say tunnels, which are again big man-made structures which require maintenance, and more we see a lot of automated systems, IoT devices, robots, and so forth being introduced into this kind of settings, and all of them require a connected application, and all of them need to work very reliably. So we'll be looking at best practices of doing so.
Yeah, so what I wanted to talk a little bit about was the device lifecycle of a connected application. There's the initial steps where you're prototyping and doing that development to get a board working. But then once the device is out in the field, there's this perpetual iterative cycle where you're going to have to dig into issues, fix and ship out security updates, address feedback and problems that are coming from your customer. And so what we want to do today is dig into what are the most effective ways to debug and fix issues at these different stages. And so we'll start by talking about local debug setup that works well with Zephyr, some of the kconfig options and tips that will help you get to fix those issues at your desk. And then we'll spend the bulk of the time about remote monitoring and how to look at what are some of the best things to look at and some of the lessons that Luca's learned shipping these products in the field. So local debug setup. The first thing, whenever I'm getting a dev board, the first thing I always want is a reliable way to attach a debugger to it. You always want a little bit more than just printf debugging. You want to be able to investigate look at local variable and global variable states, read and write memory. This will save a lot of time as you're going. And so the three things I look for in the setup is reliable setup, a setup where I can update register or memory state, and then one that allows me to script common operations. If you're doing initial bring up, there'll be classic issues you'll run into, mutex related issues, heap issues, wanting to walk through lists. So scripting that's going to save a lot of time. The setup I use with Zephyr is been Seger's JLink plus JLink GDB server plus GDB. And with Zephyr, it's really easy to get all of those wired up with the dev board. There's a package manager tool called West, which facilitates this process, fires it all up for you. There's a few extra arguments I usually like to use just to kind of see how things are running. So the verbose option will show me all the arguments that are happening under the hood. So if you wanted to start the GDB server yourself or see what options were being configured, that will print out. You can force certain runners. So there's different backend debuggers that can be used, such as JLink or OpenOCD. So I always like to force it to use the JLink setup because I found that to be the most reliable. And then I'm a huge fan of the Python GDB scripting API. This is a API on top of GDB that lets you script common operations in Python. The default GDB doesn't have that included, but you can very easily pass a GDB argument with -py to fire up a GDB with that situation. Once you're able to kind of attach and debug the board, you also need to be able to flash the board. That's also really easy to do with West. There's a West flash command. But another tip or trick I like to do is if I'm kind of rapidly prototyping and debugging and looking at things, JLink GDB server also has the ability to load or program flash itself. So if you rebuild a binary and you reset the platform in GDB, and then you type load, it will rewrite those sectors and flash for you. So that can save some time. So you have the ability to attach a debugger, have the ability to flash it. The other piece that is useful is looking at the logs that are printed by Zephyr. There's many different terminal emulators and pieces out there that you can use. The one I usually go to is PySerial, which can be installed very easily with pip and works on Windows, Linux, and OS X. And by default, you just kind of can pass it the arguments of your baud rate, which on Zephyr, the default is 115/200. And you're up and running, and you'll start seeing console logs and things like that print. So with the basic tool set in place, there's a rich set of kconfig options in Zephyr, as I'm sure folks are aware. I've tried to find the right combination of ones that save time and kind of give me the information I need while I'm debugging. And so there's a few I always like to make sure are enabled. The first one is for thread awareness. This will give you the ability when you're halting your debugger to see the active tasks in the system. And this can be really useful for digging into relationships between tasks like deadlocks or other drop that's happening. And that can be done with the debug thread info kconfig option. Used to be named OpenOCD support, but now it works with both JLink GDB server and OpenOCD. With that kconfig option in place, the other thing that can be useful is that low-level debug or being able to print information. And that can be set with the config printk option. That's the lowest level logging system on the platform. It prints directly to the console that's enabled and has minimal overhead. So if you're just trying to trace flow or look at parts in the system, printk logs can help you look at things quickly. And then on top of that, there is a rich logging subsystem in Zephyr. I always like to make sure I enable this when I'm developing because there's a lot of error and warning logs, especially in the network stacks and drivers, that will give you information about how you may have misused an API or what was happening incorrectly. So the two flags I always flip on are the config logging and the config shell. The shell gives you a way to register CLI commands and add new pieces of information. And then there's two main logging modes that can be enabled, referred to as the deferred logging mode or the immediate logging mode. Deferred logging mode will let you buffer up logs and then they'll be flushed out on a lower priority task. Or immediate mode will print the logs out directly as they're done inline in the code. When I'm initially doing debugging or development, I like to flip on the immediate mode so that you can see those logs right away and they don't, if you're printing a lot of logs in deferred mode, it's possible they roll and you don't see them in the first place. And most applications will work fine with that enabled. And so I usually start there so that I'm guaranteed to see the logs that are printing. The one thing about the logging subsystem is it usually enables something that consumes a bit of power, a UART peripheral or RTT backend. And so you really want to make sure that if you're doing a low power application, you disable logging before you ship, or you will have you'll have some power ramifications. The logging module subsystem itself is pretty neat. There's a few places or areas that it's configured that are useful to understand. Inside each module, a kconfig file can opt to include this logging template file that sets up how the levels are controlled in the system. So that's what we're seeing at the top here. And then inside an individual file, your module.c, you can use those kconfigure options to control the level that is being enabled. And Zephyr has 5 levels of logging, basically off, error only, warning, info, and debug in increasing priority. And info, if nothing is set, is the default that is there. One of the things that can be challenging, or one of the things I always look for when trying to debug a new driver or network stack that isn't working, is flipping on the right logs. And that's where a useful place I found to look is actually just the auto-generated file that has all of the currently configured kconfig options in it. And that's emitted in the build folder in this autoconf.h. And what you can do is open up that file or grep through it, and you can see all of the various logs in the levels that are set. And so if we see some that are set to 0, we know they're disabled, and we might want to enable them to be able to look at or dig into a network stack or problem. With these 3 pieces, the kind of the printk, the debugger and threat awareness, and the logging, you can usually get to that first point where the prototype is working and you're ready to start testing. And that's where remote monitoring really comes into play. There's always a class of issues that that you can't work out at your desk, or you only see once you have more than a couple of devices. I know Luca has some examples on that.
Indeed, so taking things from the desk into a real environment is always very fun and challenging, particularly because on your desk, either you build a very elaborate test setup, or you, well, test things best effort and then take things to the field and see everything that happens there. So let's look at 2 hands-on examples to set the scene again. Say GPS trackers on an animal. Let's say it's put on a sheep. The animal will roam around from, say, mobile network to mobile network, from country to country, from location to location. And that exposes the practical solution to a lot of very different corner cases. Things being misconfigured, various things happening, and we want to ensure the best performance of the solution, but also to handle all the unexpected situations. And when you get a bug report, things don't work, it's very difficult to start, right? Really testing, like, how do I reproduce this? And remote debugging allows you to immediately see what went wrong and start, okay, I know what is the issue, I can start fixing it, or at least I know what I need to mock. The particular benefit of this is when you build static sensors, which need to last 10 or 20 years in the field, is where all the faults and all unexpected behaviors will lead to a power loss, meaning that you can maybe decrease the lifetime for a decade or 5 years. And that has a very large economic effect on the deployment itself. Because of that, then remote debugging is pretty crucial to deliver a good product over time. As networks evolve, as network stacks evolve, you can test things when they're upgraded and make sure you don't introduce more problems. And Chris will tell you what's the best way to do that with Memfault.
Yeah, this is also an area I've spent a lot of time with on Zephyr and embedded devices in general, is streamlining it so you can get diagnostic information from a device up to the cloud and fix these types of issues that users are experiencing. And so one of the parts of the Memfault SDK integrates directly with Zephyr as a C SDK, and we've set it up so that the data, the packets collected, can all be forwarded over one pipe that's agnostic to the transport and use. And on the cloud side, what we'll do is analyze the issues, alert you on the issues, deduplicate problems, and let you see what's happening both at the device and fleet-wide level. And what we'll do is talk about on that side, the integration itself is very easy. It works like a typical Zephyr module, where you add it to your manifest file, and then you flip it on with some K configuration options. The SDK itself, or what we spent a lot of time on, is streamlining what properties to track. What should you look at to figure out how your device is operating and what's working. And today, what I want to do is talk about four key areas for that, and how they can be collected with Zephyr and the Memfault SDK. And those are reboot reasons, watchdogs, faults and asserts, and then connectivity metrics. I like to start with reboot reasons as a way to just understand if devices are okay. If you see a huge surge in resets on your device, it's often an early indicator that something in the topology has changed or devices are starting to experience issues due to hardware defects. And it's the smallest piece of information you can collect to start getting some insight about that. I usually break it up into two parts, or I think about it in two parts. There's hardware resets. This is when the MCU decides for you to reboot the platform. Maybe there was a brownout, or there was some phase lock loop or clock failure, or a hardware watchdog kicked in. And then there's software resets, some of which are intentional, like you want to do a firmware update, and some of which are less expected, like users kind of pushing that back button to reset the device, or resetting due to a fault or an assert. And so what we really want to do is classify what types of resets are taking place, so we can understand if there's issues that are being experienced on the fleet. And this is with Zephyr and with the Memfault SDK, this is pretty easy to do. Zephyr has a mechanism for registering regions that will be preserved across a reset. So if you're about to reboot the platform, what I recommend doing is saving why you're about to kick that off. And you can accomplish that by allocating a region of memory that won't be scrubbed across the reset, no init region. And so on the right there, I have an example of defining a file, a linker file. And then in your CMake file, you can add it as a linker source. In your C code yourself, what you have to do is set that variable in the section so that it's not reset. And so that's what we're doing in step 2 there. And then in step 3, when you're actually about to reboot the platform, all you have to do is record, hey, we're about to reset due to this. In this case, a firmware update, and then call the Zephyr sys reboot. On the other side, when the device comes out of reset and starts back up, Zephyr has a really easy way to register handlers that are invoked before main runs on the system using the sysinit macro. And so what we can do is set up a macro that captures the information we set prior to the reset and reads the MCU reset reason register. I've never seen an MCU without a reset reason register, but they all have slightly different names. But that's a really useful piece of information to collect to be able to see if there's any hardware defects or problems happening. Once the software and hardware reset reasons are known, you'll want to push that data up and send it off the device so you can start to look to see if there's any correlations or trends in your platform. Luke, I want to share an example of that.
Sure. So a very basic example we can see in the fleet is device reboots. And one of the reasons is power on reset, which really on the device should happen only when you either insert the battery or plug into fixed power. But on some applications, you can see, for example, across a fleet of a few thousand devices, there's 12,000 reboots per day. So that seems like a very large number and definitely something to be concerned with. But then again, when you check where do these reboots come from, you see there's like 10 or so, or some small number of devices to blame for the majority of them. And for sure, a device rebooting 1,000 times a day is not desired behavior in one or the other way. So in this case, it can be a mechanical bad part, for example, bad battery contact or various electronics related issues. But because you have these devices in the field already and you want to extract useful value from them, you can handle quite some of these things also in firmware itself. Meaning that tracing an issue like this, you can then roll out an upgrade which say immediately goes to deep low power sleep when the device boots, or if the reboot counter is higher than some number, you sleep say for an hour and then try to do something useful. So you can conserve battery and really kind of force the device into a more reasonable operating mode, circumventing some hardware issues that may be in place. And yeah, looking at things that can go wrong is really what Watchdogs do very well. So Chris will take you through the Watchdog implementation in Zephyr, and then we'll look at some examples how that comes in handy.
Yeah, so it'd definitely be a mistake not to ship your product without a watchdog when you're working with connected stacks or big pieces. There's a lot of things that can go wrong, and a watchdog is the last line of defense to get the system back into a clean state without an end user or you having to go and manually reset the device. So it could be things in your stack, or it could be things in the network stack. Like you could call send, it might block forever, and the device would be stuck. And so when we're talking about watchdogs, there's two things I always look for. There's the hardware watchdog. This is what's going to save you and reboot the platform. It's either a dedicated MCU or a dedicated peripheral on the MCU you're using that needs to be fed periodically, or else it will pull the reset line. But then you also need to figure out what is causing the watchdogs in the first place. And that's where a software watchdog comes into play. This is something that fires a little bit ahead of the hardware watchdog, and its intent is to do a core dump or a capture of the system state and then reset gracefully. So when you get to the other side, you know why the system was wedged. And we'll talk about how both of those can be set up with Zephyr. So Zephyr has a hardware watchdog API already, where all the MCUs that are supported, you can go through that generic API to set up and configure the watchdog in the platform. So the example we have here was for the NRF 9160, where we've gone through the device tree, and there's a peripheral called the Nordic NRF watchdog that can be set up. And then the API exposes configuration options you can set for the watchdog. What will happen when it fires? Will it reset? And then the window at which it will reset when the watchdog takes place. And then you can just install the watchdog, and you're up and running. The system is there. And what you'll have to do is periodically feed the watchdog when behavior is running as expected. Sometimes this is done from the lowest priority task. And if that doesn't fire or the system is stuck, it will trigger a reboot. The other part I like to call out, or I always look for, is some MCUs have an option where the watchdog will automatically be halted when you attach your debuggers or when you halt the system. This is a really cool feature because it makes it very easy to have the watchdog behavior, but also be able to debug things at your desk. And so you have to check to see if it's actually supported for the peripheral you're using, but it's an option I always like to configure. And then we have the to-do here of actually implementing this software watchdog API I'm talking about. And what we do in the port in Memfault, or what you can do, it's very easy, is making use of kernel timers for this, where those are powered by a timer peripheral. They can be set to just basically, to set it up, you register it, you set the timeout to be a little bit ahead of your hardware watchdog. So if your hardware watchdog was 60 seconds, you could set this to be 50 seconds. And then you're just going to feed it in step with whenever you feed your hardware watchdog. And when it's fed, it will just restart the timer. And then if the callback is ever invoked, you can just trigger an assert, which will take us through the Zephyr fault handler, which we'll get to in a moment. And we'll be able to get some information about what was happening at that point in time when the system was stuck. The other feature I wanted to call out that I'm excited about in the next Zephyr release is what's called a task watchdog. This makes it far easier to register watchdogs to monitor each individual task, where you can confirm that they're running versus just this one watchdog that you have to figure out where to feed in all the different places. So that can be a great way to make sure that multiple tasks with different responsibilities are working as expected. And there's a lot of different reasons or situations where you can run into watchdogs. I know Luca's seen some interesting ones.
Yeah, here is a cool example of what can go wrong without ever seeing it in device testing. So you can see timing defects and pretty much degradation in SPI driver chips for Flash, for example. And this you can see after a year or two, say, in the field, where you suddenly start to get stuck in SPI transactions or various bits and pieces of code. Obviously, a watchdog will catch that. But if you just get a reason, hey, hardware watchdog reboot, then you're none the wiser. So actually having the whole trace here that that's pretty much which line of the code trigger that helps you really easily find the culprit of this and work out the solution. Just an example, we've seen, say, SPI flash failing on 1% of devices of the fleet some months after deployment. Driver fix was rolled out, and the problem is very efficiently resolved, and the number of reboots is gone. So this is really a combination of good practices we've seen, which is through faults and asserts, so creating different events which tell you exactly what's happening in the field. So that Zephyr feature combined with Memfault here really makes things very practical. So over to Chris to explain how this works, and then to some more examples.
Yeah, so the Watchdog, as I alluded to, is kicking off the Zephyr fault handler via when we call an assert. If you've ever done some local debug or built some features of your own, you've probably seen a screen like this on your computer about register state when a fault has taken place on the platform. These can be due to asserts or accessing bad memory or dividing by zero or using a peripheral in the wrong way. What I want to talk about here is sort of how Memfault stitches into this path and what we were able to collect that you can look at. And so I have an example here of the fault handling flow that's taken on Cortex-M microcontrollers on Zephyr. We have some network send routine example here, where we've allocated a large buffer. We haven't checked if it was successful or not, and then we've called memcopy effectively on a null pointer. When an assert or a fault kicks off, there's an interrupt that fires on the architecture, and a fault handler is invoked on the Zephyr side. And that's in the Cortex-M case, it's called zarm_fault. And that will provide the register state at the time of that crash in the platform. And that's where those print lines you're seeing, that's where they're dumped to the console, telling you the exact state the system is in. What we do with the Memfault SDK is automatically stitch into this fault handling flow, and we'll save off the register state, the state of the kernel, and a portion of all of the tasks that were running on the system at the time of the crash into a region of memory that will survive across the reset. So this can be a piece of no init RAM, piece of internal flash, or a piece of external flash. After that's saved off, the platform will be rebooted. And the next time connectivity becomes available, all the data, the state of that system at that time of crash will be sent up to the Memfault cloud. We'll run analysis on it so you can figure out what was actually happening on the platform. So there's a few of the pieces that we'll look at there. And I think it's generally useful to look at those if you're debugging locally or debugging remotely. The first one, this is Cortex-M specific, but there's many architectures have a fault status register that will tell you why the platform asserted or hard faulted in the first place. And so we collect that as part of the crash sequence, and we'll run an analysis on that to look at what was happening on the platform at that time and what instruction triggered it. The other piece of information that you'll want to have is what was the state of the tasks on the system at the time of the crash. And so by collecting a portion of the stacks and the registers that were running on the system, we can recover exactly the line of code that the system was running on before the crash and the state of all of the other tasks. So especially in a Watchdog case where you could have a deadlock or some weird blocking between things, you really want the state of all of those tasks to see what was happening. Every platform has a set of variables or global or static variables that are useful to look at when debugging. The one we always collect by default is the underscore kernel structure in the Zephyr RTOS. This is sort of the brains of what is actually happening with the scheduler and what's running on the system. And so that can be looked at to see what threads are ready and how long they've been running and what's going on. If you're working with a connected application, often you'll want to collect the state of your Bluetooth stack or your LTE stack or parameters that were negotiated. And so any regions that are collected on that side can be shuttled up and sent over. And yeah, so you can use that information to proactively fix and look at what's happening on your device. I know Luca has some examples there.
Indeed. So one of the best practices to start off with is creating events and traces on all the code paths that should not be happening but are nicely handled in the code. For example, we can gracefully handle accelerometer faults when the communication with the accelerometer fails. So that's an example of a non-critical fault where we get a trace where that happened. The devices will recover, the next read cycle will work just fine. But we're really after the information first. How many devices does this happen on and how often? So we see if this is critical or not, and does this affect normal operation or not? And for example, this particular issue in a particular batch, we've seen, say, 3% of devices. Not critical, reasonably low priority to fix, but again, it's nice to be as bug-free as possible. And here we really see in which I2C read line things went wrong. Next example is a more evolved one with the SIM card. So that's interesting for the connected applications, because if your SIM card fails, when you have the mobile network, you don't really have any connectivity. But that might not be a permanent fail. So what we see and then normally handle with a reboot is if there's no SIM card, you may want to reboot again and so forth, and then it starts working. The practical part of how Memfault implements this is that you can save these traces in RAM such that, if you need to handle things that fail, you can still get that trace later on. So here we get the SIM card fault via the mobile communication through a working SIM card at a later point. So we see again on how many devices this happens, how often, and at what point in the code. For this one particularly, it's a hardware-related thing. You see it on a very small percentage of devices, so that's something we simply monitor and track, but not very actively resolve. Taking this further to a GPS fix, however, gives some more interesting insights. A GPS fix failing on a GPS tracker is nothing unusual, because the device might be indoor, in a tunnel, in a parking garage or so. But at the same time, we want to get specific details on how that GPS fix failed. For example, the logs feature here gives us a good way to send some raw data. In this example, in the message we see which satellites we see at what signal levels. So actually here we see that the device is seeing satellites, but their signal level is a bit too low to get a reliable fix. Now this comes in very practically because we can tell in which software revision things were better or worse. If we roll out fixes, we can see how many of those GPS failed or passed fixes we get. Taking this even further, NB-IoT modem GPS rate. Someone is not on mute. Hello, may I ask everyone to go on mute? Thank you. So the example of NB-IoT modem connectivity interacting with the GPS part, so on NRF 9160 from Nordic, you can't use both at the same time. So because modem has higher priority than GPS, it can get interrupted. And we create traces that way, so we see how often does our GPS logic get interrupted by the modem, because we want to design the application code in such a way that this should not ever be happening. And then we add a mechanism to prevent this, and we see no more traces. We get the statistics, and we can say this revision fixed exactly this issue as such. But given that there can be quite a lot of things going on when you're out in the field, there should be a good way how to prioritize things. And Chris will show a good example how we can look at the statistics for this.
Yeah, and it's one of the things where once you have that remote debugging capability in place, adding some asserts on unexpected code paths and pieces is invaluable for fixing issues. I remember I once worked on a project where when there was a failure with the Bluetooth stack, we would just kind of stop running that task and not reboot the device. But the manifestation of that was Bluetooth wouldn't work until someone completely reset the device. And so adding some asserts to get back into a good state can really help you out there. And what we have here is with the Memfault UI is a way to see kind of all of the crashes that are happening, how many devices are being impacted, how many times they've been seen. And so you can prioritize and fix issues based on that. Of course, not all issues on connected applications are crashes or watchdogs or reboots. Many of them are marginal or sort of connectivity issues in a certain location or environment. And that's where you really want to have some metrics in place to understand how things are happening on your system. Metrics that I typically track and recommend tracking are things like the CPU utilization, connectivity parameters, heap usage, and so you can start to build a pattern of what's happening on the system or what is taking place. With metrics, what you can do is then look at comparisons across your devices and across your fleet and firmware updates to understand if changes are having an impact. What we've done with the Memfault SDK is added a very easy way for someone to start defining metrics on the Zephyr side with 2 lines of code, basically one that defines a metric. So in the example here, we have a metric LT disconnect that's defined. And then another line where when that event takes place, this metric can be incremented and it will later be flushed up to the services. What we'll do on the Memfault side is compress the data down. So dozens of metrics can be collected in tens of bytes of space. We'll then index those metrics by device and by firmware version and expose that in our web interface so you can easily start to look for those trends and correlations. And I know Luca has some interesting examples of metrics that have been powerful for figuring out how things are working on LTE and GPS.
Indeed. So for example, the basic thing we should always look at in all battery-powered applications is how much time is the modem on? Like how much activity do we have and how is that impacting our battery life? So the 2 metrics we track is connected and connecting. So the connected metrics means is once you are successfully connected to the network, how long are you actually sending the data, however much data you have, and how does that duration change over time. And the connecting part is how much time does the modem require to connect successfully to the network. So tracking this too gives us a good insight. Yes, things change over a while. Sometimes it's longer, sometimes it's shorter. This is the average. And when we roll out fixes, we see, yes, this release fixed this or decrease the time by 10% or so, which is exactly what we're after when we want to optimize fleets of devices deployed in the field. Obviously, things aren't as easy always. So we look at base stations in more details, particularly for the PSM modes, so power saving modes in low power operation, where we can use the combination of creating event traces. So for example, we create a network status event trace where we parse like raw outputs from the NRF9160 modem, which gives us like cell tower information, signal levels, settings, timers, and so forth. And this we only do once the device connects. Generally, we should not see too many connects per devices, so that's a good one to track as well. If you're in PSM mode, in theory, you should be always connected, but in practice, you do reconnect every once in a while. And at the same time, you can take some of these values and then put them in a metric. So for example, the PSM tau timer, we see on the graph here is just a flat line because the value never changes. And this is exactly what we want. But in certain cases, you see when this value starts changing, it will mess your low power operation or devices will start behaving differently. And using the alerts function where you pretty much monitor the metric for a change, it's very easy to automatically see and then go and correct either the settings or new firmware revision. The most painful parts in mobile connected devices is correlated to the mobile signal quality and the signal strength itself. So that's something we should always monitor, looking at the signal level and looking at the signal to noise ratio, which both give us a good indication of what's the quality of the link. And then we look at how does this quality of the link actually correlate to bad coverage, and how can we be smarter in firmware to handle bad coverage situations. So the following example I have here is of bad coverage. We spent in this particular application a few seconds sending a few bytes of data. Typically, that's in the range of 15 seconds. So not too long, quite reasonable, and we know what the power consumption of that is. But as we can see on the metrics here, there's an example where the connected time has jumped up significantly to 250 seconds. We're still sending a few 10 bytes. But we also see that the metric for signal to noise ratio dropped significantly. And that tells us, well, maybe we should actually have been sending data at that time, because such conditions just burn through the battery and they don't send us much useful data. So because of that, then we can create different logic when we see events like this, say only if SNR is better than X, Y, or Z, send things or timeouts after, say, 30 seconds of being connected and retry some other time instead of spending a few minutes really trying to send things out. The part where testing large fleets of devices gets very difficult is where you need to automatically validate what you do in various releases. So data size is a good starting point for that, to see if you don't do anything stupid, so to speak, that you aren't suddenly sending way too much data, which would increase your device connectivity cost, which would burn more battery or do something strange. And that's a very good indicator of seeing how things typically behave and if you have outliers or not. But also that is not enough in all of the cases. So if you want to be really sure about certain applications, we can do something like automated testing. And this is very difficult to set up in most cases, particularly because you need to write very good tests, repeat them, and make sure the testing process works and also that it delivers the results to you. So the remote debugging setup, particularly through Memfault, is very practical because you can use it in, let's say, a bit more creative way. So you have your on-device metrics, traces, hardware reboots, and all that, which you track through Memfault in a normal pattern. But also at the same time, you can use an external device, say, Raspberry Pi, turning on and off the charging or turning on and off the battery voltage, or changing some parameters. Like a very simple script can introduce disturbances to your device. And what you can use is the REST API to send the test inputs to the same device ID, pretty much that the device itself is reporting. So we can see when the test jig created something, how the device responded, did you get any issues on that point? So you can really put the two in pair, and from that you can work out issues much quicker than trying to figure out, okay, we see something happened, we don't know why or what caused it. So with that, I believe we're at the end of the presentation, and we can take some questions, do a bit of introductions of us as well. So maybe let's do questions first, and then we can talk about ourselves.
Yeah, let's do that.
Okay, so do we have any questions for Chris? I've seen a few things in the chat, but that probably got answered already. So feel free to type it in. I'm not sure, maybe you can even unmute yourself and ask the question if you wish to do so. Yes, we don't seem to have questions just yet. I have one for you, Chris. Is there a good way to test things out we've been talking about today, to play with Memfault and so forth?
Yeah, so I'll skip ahead a little bit. So the features we talked about today, the repo that is integrated is available on GitHub at Memfault/Memfault firmware SDK. We have integrations from Zephyr 1.14 up to 2.6. where you can start to look at the issue analysis, the task awareness, and collect those metrics. There's a link in the deck if you have it open, where you can actually download it and try it out on your device yourself. The Memfault free trial link right there. And then I also link some of the interrupt posts that we've written on our blog about topics such as watchdogs and exception handling, if you're interested in learning more there.
I see there is a question for a free plan for Memfault. So I believe there is a free trial, as you mentioned.
Yep.
And there's a question if this is a software as a service solution, or can this be self-hosted as well?
Yeah, this is so that we take care of this is a software as a service solution. So the SDK you can integrate on the product, and then we can analyze all of that on the cloud.
So there's a further question, Chris.
Yeah, I'm very excited about the core dump feature in Zephyr. So this was hooked in before that existed, and so it's grabbing basically when the exception takes place. There's a handler that's saving off and doing that. What I would like to do is just save this off as a data format in the new core dump handler in future versions.
Perfect. Thank you. Does anyone have any further questions for Chris or for myself about any examples or things we've seen in practice? Well, given we have a few more minutes, I can maybe talk about what we build at IRNAS and what technologies we use and why we use Zephyr, because that's also some good reasoning, and then we can do some interesting discussions. So here at IRNAS in Slovenia, we apply scientific knowledge to create new products and solutions, particularly in the field of IoT engineering. So we really like doing things in open as much as possible, as we come from the open source background, and that's why Zephyr is really where we like to be heading with our device development, and also contribute to everything we find either directly through code contributions or more like in best practices and experiences we see. So from that we go end to end in the product development. What's maybe more interesting is looking at the technology map we have, which we use pretty much in Zephyr to combine different things together. So we run most of the projects on Nordic Semiconductor boards. And in the image in the following slide, you will see the technology map we created, which shows mobile connectivity, LoRa connectivity, Bluetooth, Wi-Fi, and a few other things, all nicely running on the Zephyr RTOS, because we see it's time to make things also portable, more usable from project to project. So everything is nicely software defined, and we have a good development workflow. And we really see this working as a treat, particularly when we need to roll things out, say with the help of Memfault, where you have a large fleet of devices in challenging environments, and you need to debug them efficiently. So all the tools and good practices we can get really help us out to build solutions like that.
Yeah, and in general, you can find me in the Zephyr Slack too. But in general, I'm always interested in how people are thinking about debugging devices in the field and what they'd like to look at. And so I'm always excited to brainstorm and talk about those topics. But it's really cool to be able to stitch into Zephyr, which already has a lot of the infrastructure in place, and then set this pipe out so people can look at it.
Yeah, I think it's also worth mentioning that a lot of things Memfault is putting out, it's all in the open. So there's a lot of good practices you can use regardless if you use Memfault or not. And certainly we in the IRNAS side learned a lot from this best cases of doing things. So thank you very much for that.
Thanks. There's no other questions or no other debug topics folks want to talk about on the fly, we can wrap things up.
Chris, I believe that's
Great.
it for today. So thank you everyone for joining.
Thanks everyone.
Thank you. Bye-bye. Thank you.